This is basically the equipment that's going to be used for the parallel and series capacitor lab. And so let's start out just taking a look at a capacitor. And now moving in on a capacitor. The writing is on there so that the group that has used this before would be able to keep track of it. And this is the capacitor right here, is what I refer to as in the lab as a button capacitor. Most capacitors look like cylinders, at least most of the ones that I see look like cylinders. But this is the type of capacitor that we'll be using, and most of them are about 100 nanofarads. We have a power supply for supplying the voltage, the DC voltage. We're going to use the LabQuest instead of the digital multimeters to measure the voltage across the capacitors, because basically when you're measuring the voltage, it's done a snapshot at a time, and the voltage, as soon as you hook the leads up to it, whether it's from the multimeter or from the LabQuest, you basically provide a way for the current being stored on the capacitor to start to drain. And so you'll see it definitely on the graph there, but it requires, if you're using the multimeter, to hit it at just the right moment, because this is taking measurement readings potentially 60 times a second, and that's just not enough. And I noticed that when I used this over here in a trial run, that sampling 100 times a second tends to seem to be getting some pretty decent results there. And you'll see it when we get there. And for wires, using radio jack wires with alligator clips at the end. And that is the equipment. So we'll be using the multimeter a bit in this, especially for measuring capacitance. Now there are two leads coming from the multimeter. We have a high side and a low side. So this is a traditional color convention that we use. And so common is the low side right there. And so if I want to figure out what the voltage is on the power supply, then I need to hook this to the low side of the power supply. And if we look over here at the power supply, we have red is the high side, so I have a yellow wire connected to that. Green is the low side, or I have green connected to the low side, the black lead right there. And so that would come around. And so I need to hook my probe to those. So let's do that. So I'm taking the low side probe and connecting it to the low side of the power supply. And then the high side probe connected to the high side of the power supply. And power supply is off right now. So let's measure voltage, and it should be measuring something really small right now. Notice that's millivolts. And let's turn the power supply on. So we have a voltage of 6.25 volts. And I want that down a little bit because I'm going to be using the LabQuest, and the LabQuest differential voltage probe has a limit of 6 volts. It will go a little bit above that, but I really don't want to test to see where that limit is. So I'm going to bring this down to under 6 volts so that the probe can handle it without any problem. All right, so that is the voltage that we'll be using from the power supply. And so other voltages should be based upon that. We're going to take the first capacitor right here and measure the capacitance. To do that, we bring in a multimeter, and the capacitance symbol is right there. And it is measuring on nanofarads to start with. And this is sort of a default capacitance. Now the capacitance, the actual capacitance of the capacitor is enough so that this is basically in the order of 1,000th or 0.1%. So we're going to ignore that as having any substantial impact here. And so I take my two leads and I just put them right on there. And I keep them pressed with my finger. We could use clamps if we need to. And we'll just check out the difference there. So that's 104.1 nanofarads. See a little bit better right there. And now let's use clips just to see if that makes any difference. All right, so that side is clipped. And then clipping to this side over here. And it does make a small difference right there. So to be consistent, why don't we go with the 103.1, and I'll just be using the alligator clips for future measurements. So at this point, I'm going to hook it into the circuit so that we can do the next part of the video. So I have the power supply, the yellow wire here with the alligator clip is hooked to the high side of the power supply, and the green wire with the alligator clip is hooked to the low side. And when I say high side to low side, that's high potential, low potential. The potential difference we already measured, that was the 6 point something volts. And so this is hooked into, cruising around to the capacitor. So current's going to be flowing around here onto the capacitor, and then current flowing from here into the low side. In reality, it's electron, in terms of things that are actually moving, electrons moving this way, setting up on the one side of the capacitor, forcing electrons off the other side, which then flow that way, because current and electron flow are opposite directions, sometimes referred to as traditional current, as opposed to just plain old current. But when I say current, I mean traditional. So I'm going to connect a yellow wire to that one. This is not the same yellow, this is a different yellow wire than I had before, and then hook it into the high side. And then I'm going to take this green wire and hook it from probe, or lead, probe, whichever one is the right word, to the low side. And so now you can see that from the high side of my meter along here into the high side of the capacitor, and then the green wires, one goes to the power supply and the other one curls around and connects right here. And you can see the voltage across the capacitor while this thing is on. And let's let that stabilize some. Now, part of the trouble I'm having with orientation here is I have to charge the phone while I'm doing this, and that cord is causing an extra, what looks like a twist right there. So let me rotate that a little bit. Because I have the high side of the probe connected to the high side of the capacitor, which is defined by connected to the high side of the power supply, notice we have a positive voltage there. So now I'm going to switch the leads so that the high side of the probe is connected to the low side of the capacitor, and the low side of the probe is connected to the high side of the capacitor, and we get a negative value. Now the voltage should be pretty much the same. Sometimes there are eccentricities in physics, but you should be getting the exact same value. Now let's do the same thing except with the LabQuest. Pull this off to the side. So I have a LabQuest. This is a previous trial that we are going to ignore, or happens to be on the screen. I'm taking my two probes here. I've got the high side of the probe and the low side of the probe, maintaining that same convention. I'm going to hook the red one right here, to the high side of the capacitor, and the black one to the low side of the capacitor. So just a quick glance at that. So again, high side, this yellow wire goes to the high side of the power supply. Green goes to the low side of the power supply, and so I have the red clip for the differential voltage probe connected to the high side, and the black one connected to the low side. Now notice if I start this, I turned it off not too long ago, and we're still losing some voltage. It does take some time in order to actually zero out, and that's close enough to zero. Well, let's just redo that. So I turn it on, and we get a voltage across there that is really near 6 volts, as I would expect, and that's pretty steady at the moment. So I'm going to stop that. Now notice that the current's flowing around, it gets to here, and then it starts to charge the capacitor. But once I put the probes in here, I'm starting to drain the capacitor, because the charge that's building up on it now has another path to go to get to the other side to neutralize it. And so that is a problem later on. Now, because this is in parallel with this, because I have only a single capacitor, it's not going to show up here in the voltage reading. It will show up when we get to the series capacitors, and we will definitely see that. So if we look at the high side here, actually, I don't need to do that. So let's go to Analyze, Statistics, Potential, and there's the maximum voltage. Now if there's ties, I assume that picks the first one, I'm not quite sure how it picks that one if there's more than one that has that. But we do need the maximum. That's the important one right there. All right, I'll be using the LabQuest for measuring voltage from now on. So I'd say let's use that value right there. Let's bring in a second capacitor. All right, so I'm now taking a second capacitor here, and that has a 10 on it. Whatever you want to do it. I think 10 was the original intent. And so we need to figure out what the capacitance is. So let's bring the multimeter back for measuring capacitance. I still have the alligator clips hooked to my probes or leads. So hook that to one side and then hook this to the other side. Now there's a jumble of wires here, but it'll all working out. And so this gives you an idea of the capacitance, or this gives you the capacitance of that second capacitor. And that's looking rather stable. So now let's get this hooked into series. All right, so the first thing that we need to do though is we're going to have two capacitors in series, so I need to somehow connect them. So this is the first one and the second one. So series means that current flowing into one is going to flow basically through the other one. There's no separate path for it. So I'm going to connect them right here. So I have them set up so that basically if I had a current flowing into here, it would then flow through the red wire and then back through the other one. Now it's not a complete circuit, so nothing's going to flow at the moment. I now take the probes, and you should be able to predict what the other one's going to be, what the ideal equivalent capacitance is. I've got my probe here, the positive probe. I'm going to hook it to one side. Then I'm going to take the common lead and hook that to the other side. And so now I'm measuring the equivalent capacitance of both of them. And that tells you the equivalent capacitance. Notice if I switch the lead, so basically going to put the high side where the low side was for the probe. So connecting yellow over there and going to connect green over here. And you get pretty much the same thing, if not the exact same thing. So there's no negative that pops up because the capacity meter doesn't really care about the high side or low side. All right, please go with the first value when I had it hooked up. The first, pick one. You got two answers there. Pick one. Now time to get it into the circuit. This yellow wire here is the one that goes to the power supply, and so I'm going to hook that into what we have labeled as the CD one, the one that is the first capacitor. And then this green lead is the one that goes to the low side of the power supply. So I connect it to the other end there. And now we want to measure the voltage across each of them. Now ideally the voltage, we're going to have a voltage gain going across the power supply, and then we're going to lose some here, lose some there, and then we should be back to zero. That's the ideal. It should be close. This lab works out relatively well. So first, actually, I want to show what happens here. So we're going to be measuring voltage. Connect this yellow wire to there, and the other end to the high side of the first capacitor. And then taking the green wire here and connecting that to the low side of the capacitor. And right now the power supply is turned off, but I'm going to turn the power supply on. And notice that it starts dropping very quickly because again we're discharging the capacitor, and as the charge drops out of the capacitor, the meter thinks that the voltage is dropping across it, which in essence it is. And so I turn that off. So the instructions say to do that 5 times and take the highest value of the 5. Turn it back on again. And it'd be nice if I could discharge that faster, but probably should wait for it to get down to 0. It is in millivolts. I'm probably not going to do much better than that. Now, because this samples at such a slow rate, it spikes very quickly, and then we get some pretty bad measurements. So what I'm going to do is now use the LabQuest and show some of the issues with the LabQuest, but show you how we actually can get good results with the LabQuest. So as before, I'm going to take my 2 leads here and then hook one to the high side and the one to the low side of our first one of what we're calling capacitor 1. Now I would expect the voltage to be roughly half of what is coming out of the power supply, so somewhere around 3, just shy of 3. And so I'm going to start this, turn it on, and then let's go ahead and stop that, and I'll turn that off. Now if I'm looking at the peak here, I am shy of 3, but by more than I would expect if this thing were set up right. And so do statistics, potential, and we have 2.526. We're not going to use that number, and part of the reason is that, again, it starts to drain so incredibly quickly, we need a sampling rate to match that. Right now it's doing 10 samples a second, and that's just not enough. So I click on that, change the sampling rate to, well, let's say 200, and that should get us much better results. So click OK. And then turn that on, turn that on, and it does start dropping off very quickly here. Let's go ahead and stop that, turn that off, highlight, analyze, statistics, potential. And so now we're getting a better result. Let's see if we get close to that again. So that's 2.76. Do you want to start at 0? Stop. .610. Let's do this a couple times and take the highest value. Let's wait a little bit longer for it to drain. Okay, let's wait a little bit longer to let it finish draining. I did turn the power supply off. Let's push the limits here. Can I do 400? It's still good with that. When it went into what I call the flower pattern, that's because it pulling in information faster than it can actually display it. And so that's what that was doing. Analyze statistics. And let's do one more, what the deal was with that last one. All right, so analyze statistics potential. All right, so take the highest value there. Now we're going to do capacitor number 2. So I'm just going to take these off. These, I mean the probes there, and hook it to the other one. This is the 2 reds are together there, and then the black and the green are together. And this is the second capacitor, as you can see by the mark on there. So capacitor number 2 in the series circuit. All right. All right. So I got the number there. That was 3. And let's do one more. We have that. So now it's time to set up for parallel. So we'll use the same 2 capacitors. Just need to hook them up differently. So I have the high side of the power supply curling around, hooked into one side of the 2 capacitors, and then the green side here is hooked into the low side there and into the other side of the capacitors. These are in parallel because when the current flows along the yellow wire here, it's going to get to a point and it has a junction. It can either go one or 2 paths. Because the paths connect at each end, this is known as parallel because current will split at this point, go through each one, and they can come back together here. So actually, first thing, before we turn on the current, I do need to find the equivalent capacitance, and I need to do that while it's not connected to the power supply. So we'll bring the meter back. One side hooked to that probe, and the other side hooked to that probe. Oh, that's a lot of backlighting. All right. So I now have yellow hooked to one side, green hooked to the other. Yellow and green are hooked to my 2 probes here. We need to put this on capacitor, and so we get the equivalent capacitance. And looks like it's relatively stable there. It's still sort of dropping down. So let's set this up more hands-free. You can see it's obviously approaching some value. All right, that's looking stable. So now let's hook it back to the power supply. Oh, I spoke too soon. All right, we're going to assume that is it. I'm not going to wait around forever on that one. I'm going to take my 2 leads and I'm going to connect it to, let's see, I'm going to take capacitor number 1 and hook it across there. Zooming in, as you'll see, that's capacitor number 2 right there. So the other one, this is capacitor number 1, and the red is hooked to one side and black is hooked to the other. And this black one should not be touching this wire over here, so I'm going to adjust it a little bit, but you have an idea of what the picture looks like. All right, so let's go through the exercise again. So this is capacitors in parallel. Now notice it's not dropping off because we're measuring in parallel, so not an issue here. And so just highlight, analyze statistics potential. And it pretty much should be the same thing. I don't need to do that one 10 times. I'm going to take the 2 leads from the differential voltage probe and hook them to the other capacitor. And so this is the other capacitor. And so we have the maximum value again there. So now we need to bring in the 3rd capacitor. Third capacitor doesn't have anything written on it, unlike the other 2. So that will distinguish it. So I need the multimeter to measure the capacitance of this one right here. And so we are getting the values of the third capacitor. It's looking relatively stable, so now I'm going to hook it into the circuit. As with any time you are setting up a circuit, we do need to make sure that we have it set up right. So I've got the yellow wire here, sort of coming from the high side of the power supply into one side of my parallels. There's capacitor 1 right there and capacitor 2, and apparently I need to reconnect that. So let's do that now. So I have 1 and 2 in parallel, and we can see that that is capacitor 2 just by rotating that, and we got the familiar 10 on it. And so now, current flowing into here will go through one of these two paths, then it'll come down the red wire. This red wire will connect to one side of capacitor number 3, and then current will flow across that through the green wire and into the low side of the power supply. We need to find equivalent capacitance of all three of them. So let's get that hooked up. So I'm going to disconnect them from the power supply. So this was in the high side of the power supply, hook that there, and then I'm going to take the one from the low side of the power supply and hook that here. And we get equivalent capacitance. And that's roughly what I would expect, and so I am feeling like we don't have a loose connection anywhere. Give it a moment in case it wants to change. And that's looking rather stable. So now let's disconnect from here and hook this back into the high side of the power supply, and from here into the low side of the power supply. So now I have my circuit, and so now it's time to measure voltage. And for measuring voltage, I'm not using the multimeter because that really does not work well. Bringing in the LabQuest 2 again. Got my two colored probes here. So first one, we're going to do capacitor number 1. And now it should be dropping off because I do have a series going on here, so we will be doing multiple attempts at this. So I'm going to start that, turn that on, stop, so analyze, statistics, oops, oh yeah, there we go, there's the high and the low. I don't need to highlight really, it's just going to take the whole sample set. So that is the maximum across capacitor number 1. Let's do that again. Analyze statistics. All right, so this is number 3. And then shoot for number 5. All right. Now doing that was capacitor number 1, so now capacitor number 2 should be getting very similar results to capacitor number 1 since they are in parallel. Third one. Fifth one. All right. And now to measure the potential across capacitor 3. So this plus the other one should give us a voltage that's very roughly equal to the voltage across the power supply. Trial number 2. Trial number 3. The reason, again, that we're doing 5 trials is that because this is sampling at discrete times, if we miss the peak, then it's going to throw things off. And so I wanted to do it 5 times. We have a better chance of actually catching the correct peak. So 4, I believe. And then 1 more to go on this. All right, so that should be the 5 trials. And for the last part, we don't need that. We have the capacitance of the first 3 capacitors right there, so 1, 2, and 3. I'm going to find the capacitance of 7 more capacitors, and you are to figure out how you need to put them in series or parallel. Unfortunately, you can't really do the experimentation, but should be able to at least calculate it. And so follow the instructions based upon this. You're still targeting for an ideal value that is close to the 75 plus or minus 5 nanofarads. Based upon assuming that the values that I'm about to give you are all perfectly accurate. So this will be capacitor number 4. All right, so that's capacitor number 4. Capacitor number 5. Capacitor number 6. Capacitor number 7. Capacitor number 8. Capacitor number 9. And capacitor number 10. And using 5 to 10 of these capacitors, you want an equivalent capacitance to be 75 plus or minus 5 nanofarads. Please make sure you indicate where to put the probes so that there it is. You have all the information. And don't forget, rejoice, because this is physics.